Hello guys, welcome back. So in this today's class we are going to learn about the floating point representation, so which is the first unit topic. So for example, see how to represent the given binary format in terms of the floating point representation. Once it is completed, then we will try to solve the problems, right? We will try to consider some problems so that we will find the solution in terms of the floating point representation. Suppose for example, see that the given binary number is something. So here we have the, right, so this dot, so 4101 dot 1000111, so represented in the floating point format. So if you want to represent in terms of the floating point, what we have to do is this number, see that in floating point number, first binary point is shifted to the right of the first bit. It means that this point should be shifted to the right of the first bit. So it means that here we need to place the dot. So see that what is happening, this is the value 14141, right? 01 dot 1000110, right? So here we have the dot, it should be shifted to the first one. So after shifting the dot, so what is the value? This is something, right? 11101. Now dot will go to here, right? So what is the remaining value? 000110. So how many times it has shifted the value? 1 2 3 4 5. So this is what we are going to represent in terms of the exponent value. This is a scaling factor. Remember that always scaling factor should be 2. So how many times you are shifting towards this direction? So in this case, if you want to reach here, so how many times we need to shift? 1 2 3 4 5. So that this is the exponent value is 5, right? So try to understand this one. This we are going to use when you are solving the problem by using of the floating point representation method. See the same example here we have given something, how many times we are shifting to reach 5. Suppose for example the given number is something like this, 01.111 something. Now how many times we need to shift? 1 2 3 4 5 6 7 8 9, right? So it means 1.1233 something, 01111 something, means how many times we shifted this value to reach to the first point? 9 times. So it will be, we are going to write in terms of the 2 power 9. So here how many times we shifted? 5 times. So here the value will be something, exponent value is the 5, right? So what is the meaning of this one? Means suppose if you see here, so this is the value, right? This is the dot, right? This is the last bit we called as the sign bit value. As we know that if 1 means sign bit value, it is the representation of the negative number. If 0 means it is the representation of the positive value. So this is what the remaining values we called as the Mantissa value. Then what is the exponent? How many shifters we have performed? 5, right? So this is what we called as the exponent value. So exponent value equal to 5. Then what is the significant bit or Mantissa value? This is the Mantissa value. Then what about this one? This is the sign bit representation, which is used to find out whether the given number is positive representation or negative representation, right? So in exam point of view, they will be asking, right? So IEEE standard floating point number, they may be asking represent the given binary number or decimal number in terms of the 32 bit standard. The one way of the question is that use the single precision representation, or one more way of asking the question is 64 bit standard or double precision representation. First one is the single precision representation and second one is the double precision representation. So we will try to solve the problem. So before going to that, we need to see that how many bits are there in the single bit precision as well as the nothing but the 32 bit word, as well as the double precision means 64 bit. See that this is the total length of this 32 bit. The last bit MSB bit value we called as the sign bit. So the number of bits will be assigned for the sign bit is the 1 bit value. Then remember, for exponent we are going to assign the 8 bit value representation. Then remaining bits are we called as the Mantissa bit value. So if you want to solve the problem based on the 32 bit or single precision method or double precision method, we need to remember this one. So first bit is the MSB bit is the sign bit, remaining bits are the 8 exponents bit. From here to here it is called as the Mantissa bit value, nothing but 23. So to 23 plus 8 plus 1, nothing but we have the 32 bit length, right? Now see that, so this is the sign bit value. This value we need to find out. Later on we will see how to find out this value as well as the this value. But remember that, so if you want to find out this value, E bar value, exponent value means, right? So this can be find out by using of the scaling factor. We will see what is the meaning of scaling factor. Plus if it is 32 bit representation means we need to add, for that particular bit we need to add the 127. If something it is the 64 bit means, if you want to find out the E exponent value means we need to add the that scaling factor plus 1023. Remember this, the bias value should be added in order to find out the single precision or double precision. So it means something 8 bit means 8 minus 1 something, it is 2 powers and 256 values something, right? So 259, 128 bit value, it means that 0 to 127, like that we are going to add the 127. So first we will try to see that, just try to remember this one. Once it is completed, this is the 64 bit, right? So 1 bit is sign bit, here there we have the 8 bit value, here we have the 11 bit value, the remaining bits are used for the mantissa. Then how to find out this e value? This exponent value means this is e value we are going to find out. For that we need to add the bias is nothing but the 1023. In case of 32 bit or single precision means we need to add 127, that bias value. In case of the 64 bit double precision means we need to add the 1023, right? So first field bit indicates the sign bit value, then this field indicates the 11 bit is exponents, then third field indicates the mantissa value. Now if you don't understand, first we will try to take the problem so that you will understand. So what is the given question is that this is the decimal number system which need to be represented in terms of the single precision as well as the double precision by using a IEEE floating point representation. So single precision means 32 bit, double precision means it is the 64 bit representation. The one way is that, what is the first step is, either it may be whatever the number system it will be having, the first step we need to convert in terms of the binary representation, right? So 125901. So for example, how to find out? We have the two things, right? 263 point t means this is the integer part, this is the fractional part, right? Integer part can be solved by using of what? Division method. Fractional part can be solved by using of the multiplication method. Now see that 263 is my binary representation, 0.3 it is the binary representation for the fractional part. Now just you add the integer part plus fractional part, so that number will be converted in terms of the binary representation. See that this is the binary representation for the integer part 1259, this is the binary representation find the 0.125. Now this is the integer part plus fractional part, this is nothing but your binary representation. So first step is that if the given question is not in terms of the binary representation, first we need to convert in terms of the binary representation, right? Once it is done, as I explained in the previous, so out of this one what we have to do, where we have the dot here, this one, right, we need to make here. Now how many shift we need to perform? 1 2 3 4 5 6 something, right? So I have missed somewhere, right? So 1 2 3 4 5 6 7 8 9 10. So these many value we need to shift, right? So actually where we have this dot here, now if you observe here, here it is, right? So but here we are making here, right? So it means that in between how many bits are there? 10 bits. So what is the exponent value here? Remember the exponent value is the 10. Now see that this will be converted in terms of the this representation. Now if we see that what is the sign bit value, last bit value, right? So if it is 0 means it is the positive representation, if it is 1 means it is the negative representation. But see that what is the given question, positive number or negative number? Positive number. It means that sign bit value should be always positive, representation means 0, right? Now see that what is the how many exponent value we got? The exponent value we got is the 10 values, right? So if you remember this one, this is important, sign bit value as well as the exponent value. So this is for 64 bit, right? So sign bit value, remaining 8 bit values, so 23 bits are the mantissa. As I told that how to find out the e bar, we have find out e value, right? What is the t value? Exponent value 10. So what we have to add? We need to add the 127 in case of the 32 bit. In case of the 64 bit, we need to add the 1023. Now we are solving the problem for what? 32 bit, right? Now what we have to do is, this is the e value we got something 10, right? Now see that how to find out, this is the first field, right? Sign bit value. What is the sign bit value? It should be 0. So next this is the exponent value, right? So e bar we need to find out, right? That is nothing but e plus 127. So what is the e value we have obtained? E equal to 10, right? So 10 plus 127 is nothing but the 137, right? What is the binary number for 137? 100010001. So here we are writing that 8 bit representation as the 100010001 something. So this part we have completed. Now we need to write this value. How to write this value means, right? Now see that. See, this value is nothing but what? The remaining length is nothing but the mantissa, right? So what you will do is, this is the value we got, right? Mantissa value. See, after converting this one, this is the Mantis value we got, right? Nothing but same this value, right? Just to copy this value 0 0 111 0 1 0 1 0 1 1 1 0 up to this one, because it is the 23 bit representation, right? We don't have the 23 bit representation, right? We don't have the 23 bits. So what we are going to do here is just we are going to write this number as it is. So this number will come up to here. After that we don't have the number, so we are writing the 0 0 0 0 something like this. This is how we are going to solve the problem by using of the single precision method or 32 bit representation, right? Now see that if you want to solve the same problem using the double precision method, means only the thing is that earlier also e equal to 10, right? So here 10 plus what we have to do, we need to add the 1023 for 64 bit. Now 10 plus 1023 means 1033, this is a binary number. So earlier it is 8 bit representation, right, as per the format. Now it is the 11 bit representation. That 11 bit representation we are copying. Now what is the Mantis value? This is the Mantis value, right? Just we are writing this value here. So next onwards, if you don't have any value, means just we are writing the 0 0 0 for remaining all the bit value, right? So let me take one more problem so that you will be understanding. This is the given question which we need to convert in terms of the IEEE 754 32 bit floating point representation. First convert this number into the binary representation. Now where we have this dot here, right? Now shift to the one position to this number. How many times we have performed the shifting operation? 8 times. Now what is the e value? E value equal to 8. So in case of the single precision, means e bar, this value equal to e plus 127. So what is the value we got? 8 plus 127 is nothing but the 135. This is the binary number for this one. This is given number is as per the question positive number, right? This value equal to 0. This 8 bit value is nothing but 135. The remaining bits are nothing but your Mantis value. This is the Mantis value we have obtained, right? You just copy this value as it is. If empty locations are there, you just write the zeros. If it is 64 bit, means instead of this 127 you take the 1023.